Good afternoon, everyone. This is my first attempt at doing a webcam for remote instruction. This is for statistics. This is Chapter 8. It's on sampling distributions. Chapter 8 covers, 8.1 is on the sampling distribution when we're looking at the mean of a sample. And 8.2 is when we're looking at proportions. And we're gonna look at similar stuff. So for mean of a sample, this semester I have 3 stats classes. Okay, and I could take the mean of each class for the midterm. I have 3 stat classes this semester. I could calculate the mean for each midterm. The mean midterm score for each term or each class. All right. Now, the odds of them being the same are extremely improbable. The likelihood of all 3 classes, or even 2 of the classes, having the same mean is highly unlikely. I realize right now that I have no one able to respond to me. We'll do a live version of this soon. Wanted to get you caught up. So while you're watching these videos, just hit pause if you need to stop and write down what I'm writing. And I do have similar copies of this stuff up. And what I'm really trying to point out here is, since the sample mean can change depending on the sample, then the sample mean, X bar, is a random variable. I don't really know that I like the way this red pen is showing up. So we'll switch to using blue, black, and green for now. And since it's a random variable, it means it has a probability distribution. The red, blue, green pen doesn't want to work. I got another green pen. Sample mean has a probability distribution. See how I can tinker with this camera. I'll leave it right there for a little bit so you can finish writing it down. All right, let's go to another page. Hopefully you hit pause to continue writing if you needed it. Since it has a probability distribution, we must be able to calculate a mean. And interestingly enough, as I'm going to show you in a second, It doesn't really matter the starting shape of the distribution, whether it's uniform or skewed left or right. If we have a Poisson distribution, as soon as we start looking at multiple samples and we try to calculate the mean over samples, this ends up following a normal distribution. When we look at the mean of multiple samples. And that means we have our good old bell curve. Oh, I've done better. We've got mu of x right here. And normal distributions have a mean and a standard deviation. Well, it just so happens to turn out that, let's see how the blue pin works. The mean of the sample means, it's like a dream within a dream. The mean of the sample means, so if we take a bunch of samples, find their means, and then take the mean of all those means, the mean of the sample mean, we'll call mu of x, is the same thing as the mean of the overall population. And if we want to find sigma x is very close. The standard deviation is related to the standard deviation of the population, but we have to divide by the square root of n, where n is our sample size. Sorry, I tend to look down a lot so I can see what I'm writing. It is on the screen, but it's awkward to write looking at the screen. It's easier to look at what I'm writing at. I will pause and give you guys a chance to process that information. And we'll look at some examples. We'll even do some in-class homework assignments, problems, test it out. Hopefully you clicked pause to write this down. All right, let me start up with the next part. So think of our IQ test. Recall our IQ test. This is a little different than the notes I already have posted, but recall our IQ test had a mean for the population. Mu pop was 100. And the standard deviation for the population was 15. Let's say we look at a group of 9 people. So let's let our first sample groups, there's 9. So if we look at the mean and standard deviation for just those groups, well, the mean remains the same. The mean for our sample is the same as the mean of the population. And the standard deviation for these 9 groups is going to be the standard deviation divided by the square root of n. Now the square root of 9 is 3. This is 15 divided by 3, and it goes down to 5. So when we're not looking at the whole population, just looking at 9 groups, our mean changes? Not at all. Mu is still 100. The standard deviation, however, has decreased. Let's look at n equals 25 because I want to point out something. I want to look at two graphs and show you what happens as this n increases. It's pretty neat stuff. So for n equals 25, mu of x is still 100. And sigma x is 15 over the square root of 25, which is 15 divided by 5, which is 3. So let's take a look at that. Give you a chance to finish writing that. Okay. Let's look at three bell curves. So the overall population we have 100 in the middle. When we go out one deviation, it's plus 15. Sigma equals 15. I go out another deviation, it's 130. Another deviation, it's 145. And I could go the other direction as well. If I look at n equals 9, I want my same 100. But then now the standard deviation is 5. So where 115 used to be one deviation. Now going over to 115, that's 3 deviations. And going the other way, 15, it must spike like this. Oh, I don't even know if I can do it any smaller with 3. I can try though. Let's give it a try. My final one, 100 needs to be in the middle. Now standard deviation is 3. So 3 times that is 9. And so now I can only go 9 each way before I hit 3 deviations, which means it's got to be like that, like even more narrow. So pause for a second, let you jot that down. Now, if we look at those graphs, as n increases, the standard deviation decreases. It started at 15. This was 15. Within going to n equals 9, it cut it in a third. Going to n equals 25, it cut it in fifths. It's going down. As n increases, it goes down. If n went to 100, we would have divided the 15 by 10 and would have had 1.5. And now notice what happens to our graph. It gets really, really narrow which means the hill gets really, really tall. The hill gets really, really tall because the area underneath that line needs to be 1. If we calculate the area, it needs to be 1. So if it stops getting really wide, it has to get really tall in the middle, which means we decrease the range of reasonable answers. If we have 25 samples, it's unlikely we have anyone that's a genius or at the bottom end of the scale. If we're looking at the whole population, we definitely have geniuses. But if I only sample 25 groups, it's unlikely that I'm going to have a genius in the group. Just the way it is. So as n increases, the standard deviation decreases. Which means the spread decreases. And therefore, the likelihood of having an extreme member of the population in the group has gone down. This idea that the standard deviation, this is called the standard error of the mean. Okay, so as I was mentioning earlier, normal population distributions come in all shapes. We have like uniform distribution. This is where our graph looked like that. Each group had about the same probability of happening. This kind of stuff happened with dice rolls and things of equal probability. This one is the uniform looks the least like a normal distribution because it's flat. Then we recall we had this, oops. We had skewed left, skewed right. These are closer, they have humps. Left or right. And then we had our normal distributions like IQ, which we just did. I'll pause and I'll let that soak in for a second. All right, I'm going to turn the page. Hopefully you clicked pause. This leads to the idea of the central limit theorem. So the central limit theorem says, this is one of the biggest things that helps us throughout statistics. The central limit theorem says, regardless of the shape, of the underlying population, lying population distribution. The distribution has a shape. The sampling distribution of the sample mean is approximately normal for large enough n. The example I'm going to show you right now, you can see I have in StatCrunch a bunch of columns of data. My first example, or the example I'm going to work with right now, is dice rolls. I have 1,000 rows, 100 columns in each row. Of simulated dice rolls. Now, we could do the whole custom calculator. Remember when we did this, we could do X and P of X. We've got 1, 2, 3, 4, 5, 6. The probability of each one happening is 1/6. And mu of X was the sum of X times P of X. Okay. So mu of X equals 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6. And we keep going up to 6 times 1/6. And I can actually take these numbers on the outside and multiply them by the numerator. And this just becomes 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6, which is 3.5. Let's see if we come up with that in our simulation. I want to give you time to jot that down. I hope this new format is going to work well. We will have it where you'll be able to ask live questions. I'm just getting set up, used to using this situation with the webcam and the document camera, and I've got a fancy new microphone like I've got doing a podcast. It's pretty slick. I like it. I like it. It's not the same as being in person. What are we gonna do? We didn't make the coronavirus. We're just living with it. Now, I do want to point out it. So let me bring this back down. Hopefully you paused and wrote what you needed. We had mu of X equaled 3.5. It is impossible to roll a 3.5. On a 6-sided dice. But this represents the average of a bunch of rolls. I'll let you write that down. I'm going to make the StatCrunch screen bigger. Pause it if you need to. Okay, unpause. What happened to my data? Rude. Did I keep any of them? Wow, it didn't. That's messed up. All right, so the way I'm going to simulate this is I'm going to say data simulate. We're going to do uniform. I'm going to tell it I want 1,000 rows, 100 columns. The only way I can get it to go between 1 and 6 is say a minimum of 0.5, a maximum of 6.5. And then I'm going to tell it to round. Okay, so this generated literally 1,000 rows, 100 columns in each row. So we're going to be looking at some of the later columns. What I'm going to do is, first off, I'm going to do stats, summary stats, rows. I'm going to calculate the mean of just the first 2 squares in each row. Annoying pop-ups. So this is the mean of the first 2 rows, or first 2 columns for each row. And I'm going to tell it to store it in a new data table, or store it in the data table. And notice how it pops up over here as row mean. N equals 2. Let's look at n equals 5. I'm going to do n equals 10. N equals 25. You don't need to repeat this. I'm getting data set set up. We'll do n equals 50. N equals 50 is it's grabbing the first 50 squares of each row, calculating the mean of those squares, and it records that at the end of the row. And finally, we'll do 100. Okay. Now I said this was n equals 5. This was n equals 10. N equals 25. N equals 50. And n equals 100. Now if we look, let's go through the column 2. This is just the mean of the first 2 squares. I've got 3, 3, 3.5, 2.5. They're all even increments of 0.5 or something like that. When we do n equals 5, now we have slightly different values. We're not doing increments of 0.5 anymore. It gets a lot smaller. When we get up into n equals 25, all of a sudden we start having 2 decimal places. And n equals 100 is this. So this is what the whole idea of the sampling or the mean of the sample means is. N equals 2, I have 1,000 sample means of size 2. If I do summary stats on columns now and look at those values, hell, I'll do all of these right now. Let's look at the mean and the standard deviation. When we only had 2 squares, the mean was 3.49. It was actually pretty close to 3.5. When n equaled 5, it was 3.482. N equals 10, 3.47. And then we start getting closer. It starts just ricocheting around 3.5. Look at that standard deviation though. That standard deviation is showing us that that range is going down. For n equals 2, we have a standard deviation of 1.2. When we're up to n equals 25, it's just down to 0.33. And when we have n equals 100, it's at 0.166. Now, we can take a look at that by looking at the histograms. Let's take a look at the histograms of those columns. So I'm going to tell it to start at 1. And let's just give it a width of like 0.001. It gets pretty small in range right there. So let's go down to 0.01. And let's look at how the shape of the distribution is. In fact, if I add one more column, like doing the uniform equals 100, that's just doing the last column. That's like n equals 1. So I've got n equals 1, n equals 2, 5, 10, 25, 50, 100. We look at the distribution. Why didn't it do the 100 first? All right, so here n equals 2. Notice even for sample size of 2, since we're doing the mean of 1,000 rows, where each sample is size 2, we're already at a normal distribution shape. But the range goes from 1 to 6. Look at that. We've got a full spread all across the spectrum. Some of them had a mean of 1, some of them had a mean of 6, which meant both rows were a 6 kind of thing. We look at n equals 5, and we still have a bell shape, but notice we're not going all the way to 1 anymore. It doesn't look like we're going all the way to 6 anymore either. In fact, this is stopping at 5.6. N equals 10. Now our lowest one is 1.8. Our highest one is 5.3. We're starting to narrow in. The width of that column is getting narrower and narrower. N equals 25. Our lowest one is 2.5. And our highest one is 4.6. Now we're within one whole number of 3.5. We go up to n equals 50, 2.8 to 4.2. Now we're less than 1 away from 3.5. And it gets even tighter and tighter. Now we're going from 3 to 4. So now we're only 0.5 away for the all the results of those means. But if we look at one column, just the uniform 100, it doesn't look bell-shaped at all. It's got a uniform distribution. Those are all approximately the same height. As soon as we start looking at the mean of a couple of them now, and then doing the mean of all the means of a bunch of samples, it shifts into this normal distribution, which is really neat. It's a useful property that we're going to use. Okay? So let me move that out of the way for a second. I need to, there we go. That's what I want to do. Get that camera back up so I can write. So let's look at how some of the math lab problems look. You didn't need to do any of that in StatCrunch. I just wanted you to see what happened with the graphs. Did you see how it condensed? It got tighter and tighter and tighter. That's really the idea of what's going on here. Okay. So what math lab will do for your homework, they'll do stuff like this. They'll give you like a population mean. They may give you a population mean. And standard deviation. And then they'll give you a sample size. Then a sample size. And then they ask for mu of x and sigma of x. So recall, mu of x is just the mu of the overall population, and sigma x is sigma of the overall population divided by the square root of n. Okay? Let's take a look at one. I'll leave that up on the screen for a second. I'll pop over to MATLAB, load up a question. Let's see what we find. So this is assignment 8.1. Let's take a look at question number 2 and question number 6. Question number 2. So I'm going to write it down. And I'll switch back over to the camera so you can see what I'm doing. But I want to write down the numbers first. My mean is 70. My standard deviation is 36. And they give me n equals 81. All right. So let's go back over to my camera. This is what they give me. And they ask for mu of x and sigma of x. Mu of x is just the same as mu, is 70. Sigma x is my old sigma divided by the square root of n, which is 36 divided by the square root of 81. Now the square root of 81 is 9, and 36 divided by 9 in the calculator is 4. My answers are mu equals 70 and sigma equals 4. I'm going to go over and put that in. Let's take a look at what happens when I do. Good job. And sigma of x equals 4. They have questions like that. I also want to take a look at number 6. So number 6 is on a geyser. And I'm going to write down the data it asks me, or gives me. So problem number 6 is on geysers. And it tells me my mean time is 66 minutes. And my standard deviation is 24 minutes. Then they ask me a bunch of calculations. Part A says that what is the probability that the eruption times are longer than 78 minutes? So I'm going to write that down, longer than 78 minutes, so I can switch back to my camera and we can discuss what I'm doing here. So if x is my random variable for the amount of minutes, what it's saying is, what is the probability x is greater than or equal to 78? Well, this is a stats calculators normal kind of problem. Stats calculators normal, right into StatCrunch. I'm gonna close that window out and open up a new one. Don't need all that crap in the way. Stats calculators normal. Okay, you guys with me? What I'm gonna do is I'm gonna put in my mean is 66 minutes. My standard deviation is 24. And I want the probability that x is greater than 78. So they give it to me. I'm going to write down a few decimal places because I don't know how many I need to round to. If it's four decimal places is 3085. Oftentimes it's 4, so let's just assume it's 4 and go from there. Pause, write it down if you need to, so I can switch over to Pearson and check my answer. Yeah, it says 4 decimal places, 0.3085. Check my answer. And now question B, they change it up. It says a random sample of 8 intervals. Random sample of 8 time intervals. What is 8 right here? Well, they're recording 8 different entries. So for this, n equals 8. So I'm going to switch back to my camera. I wrote that down. Random sample of 8 time intervals, n equals 8. What's our mean and what's our standard deviation? The mean doesn't change. The mean is still 66. Standard deviation is 24 divided by the square root of 8. You just have to put that in a calculator. Where'd my calculator go? There it is. Twenty-four divided by the square root of 8. 8.48. I'll write them down. 8.485281374. And they wanted to know the same thing, the probability that x was greater than 78, I believe. I believe. Let me pop back over and check. More than 78 minutes. Yeah, that's where we're at. So they wanted the same thing. My mean doesn't change. The mean is still 66 minutes. Standard deviation, though, changed. And don't be lazy. Don't enter everything your calculator says, because you never know if not entering just a few more digits is going to make your error be off by the 10,000th decimal place. And you're going to think you don't know how to do it, and it's just because you were too lazy to enter everything in the calculator. Enter everything your calculator says. I just entered everything. It doesn't take much longer. We'll click compute, and now it's giving me the probability that x is greater than or equal to 78 is 0.0786496 to 4 decimal places, 0.786. Let's compare that to what we have above. Look at that. It's gone down. It's less than 0.3085. So as soon as we start introducing a number of, not the overall populations, but a specific set of 8, it changes. That's what we showed with the dice rolls as well. Okay. See, all they do is they change n to equal 17. Oh, I can do this. No, it's just easier. Just click back between. So C, n equals 17. So the mean is still 66. The standard deviation is now 24 over the square root of 17. I'll put that into a calculator. 5.8208555001. Changes my standard deviation over here. I think they still wanted 78 minutes. I'll double check. More than 78 minutes, yep. .62517. 4 decimal places is 0.0196. Remember the rules of rounding. Always look to the number to the right. Okay? So hopefully you're pausing and doing as you need to take notes and follow along. Rewind if you need to. All right, what's it asking me here? What effect does increasing the sample size have on the probability? Well, if we look at our calculation, as n went up, we went from 1 to 8 to 17. The probability went from 0.308 down to 0.078 down to 0.019. It kept decreasing. So that's what we need to look for. The population mean is less than 78 minutes, then the probability that the sample mean of the time between interruptions is greater than 78 minutes decreases because the variability in the sample mean, the variability is related to the standard deviation. It's the square of the standard deviation. So if the standard deviation goes down, variability goes down. And that happened as n increased. Now this last one you might find a little tricky. You have to really stop and consider what might apply. What might you conclude if a random sample of 17 time intervals between interruptions has a mean longer than 78 minutes? So we got to select all that apply. So the population mean could still be 66, and this just could be a rare outcome. It's possible. We could have drawn Albert Einstein picking a random person for intelligence. So that seems reasonable. The population mean is 66, and this is an example of a typical sampling result. Well, if it were typical, it should be near the mean, right? And we're a long ways away from the mean. It says the probability is 0.019, which means it's less than 0.05. It's an unusual event. It doesn't happen often. It's only going to happen 2% of the time, which means it's not typical. It's not typical. So B's out. Could it mean the population mean may be greater than 66? It could. That's reasonable to think. Maybe our assumption that the mean time was 66 minutes was wrong. Usually when they're doing like a geyser like that, they're just grabbing thousands of data points. They record it for a year. How often does that geyser go off? Like Old Faithful. And they come up with a mean, but maybe that year, with the entire year, was just an anomaly. Maybe the mean is greater. The population mean may be less. This is getting unlikely now. If it were less, this probability should be even lower. So that doesn't seem very likely. E, the population mean must be more than 66. It doesn't have to be more than 66. This could have just been a rare outcome. It could have been a rare outcome. If you're ever in Yellowstone's got Old Faithful. Going to the geysers, Old Faithful is a really neat place to check out. Sometimes you got to wait an hour, and sometimes it's less. It's neat seeing though. It sprays water super high in the air. It's really awesome. So it must be, that's the kicker which says no. And the population mean cannot be, This is another absolute statement. It can't be. Well, why can't it? Maybe this was just a rare outcome. So F doesn't seem reasonable. And G gives me another absolute statement. It must be. And must be less than 66. That doesn't make any sense because the probability is so low. If anything, you would argue more than 66. So the only ones that look reasonable to me are the one that says just a rare sampling and the one that says it may be greater than 66. Excellent. And then sometimes, let me see if I can find one for you. I'm not going to do all your homework for you. This must not happen until 8.2. Maybe I'm wrong. Let me go back through these. I'm looking for a specific event. Well, let me describe the scenario in case it does pop up. I think it's an 8.2, which I will do in another video, but let me go back to the camera and we'll talk about what I wanted to tell you. So sometimes they give you sigma of the sample mean, standard deviation of the sample mean, not the population, and they give you n. And they ask you for sigma of the population. Let me give you an example. This is probably easier as an example. Example, sigma of x is 15, n is 36, find sigma. Now remember, we have the equation. When it says sigma, this means sigma of population. If they want the sample mean, they'll say sigma x or sigma x bar. Usually x bar. I keep getting lazy. Recall, sigma of x bar is sigma of the population over the square root of n. What does that mean here? I've got 15 equals sigma of the population over the square root of 36. If I want to get sigma by itself, multiply both sides by the denominator. Denominator. Or clear the fraction is what else we call it. So 15 equals sigma over the square root of 36. I'll multiply both sides by the square root of 36. This is like multiplying by 36, square root of 36 over 1. And anything that shows up in the numerator and denominator, we can cancel out. And on the right side, I get sigma. Square root of 36, if you throw that in your calculator, is 6. So I get 6 times 15, or 90 equals sigma. So that's what they're doing. You can go back and figure out the standard deviation of the overall population if you know the standard deviation of the sample. And it might pop up, I think it might be an 8.2. I will open up a new video on that shortly. I hope you've enjoyed this initial test run. I am going to stop this video shortly. I will save it in a file and upload it to Canvas for my 3 stats classes. I'm going to do a few more like this, get us caught up, and then we'll start working on live videos soon, okay? Where you can log in during class time and you'll be able to ask questions live, okay? Peace. Been great. I hope you guys liked it. Let's call this a wrap.